present this lecture, to be invited to this conference, to be allowed to speak at this conference, well, I have a very daunting task of explaining two different subjects related to information geometry. I mean Castle-Wilbeck cohomology and foliations. It's about the joint work with Michel, Nguinaprawo, Boyom, who is, let's say, responsible for KV cohomology, and I'm here responsible for foliations. Well, it's a kind of sketch of the talk. So first I will give some algebraic preliminaries, then we'll continue the foliations and you see the relations of these two objects with information geometry. In a way, I have a task a bit less difficult because Professor Shima talked about Castle-Wilbeck algebras. So I have here a slide presenting, you see the definition of a Castle-Wilbeck algebra, the anomaly, and the definition. So I will, well, I have a little time, so I'll just skip it. Then we have a slightly different object in algebraic. In differential geometry, it's a very important object. Here you have a definition, slightly more general objects in the standard algebroid, well known in differential geometry. Something we call, it's called Castle-Wilbeck algebroid. So we have a vector bundle of a base manifold, and on the model of the sections, global or local, could be, depending what you want, could be global sections or the module of sections of an open subset of the base manifold. This you see objects, the set of sections have the structure of the Castle-Wilbeck algebra. There are two conditions you see which give more or less kind of a local flavor to the definition and permits to define the bracket which made out of this object the standard algebroid. And so here we have also a subspace or vector space spanned by the commutator AB. It's in the last line, last two lines, and we denote this object. It's a Lie algebra, and we denote it by script L. Well, after this preliminaries, we go to some towards the cohomology. We define a model, so we have the action of this Castle-Wilbeck algebra of a vector space W from the left, from the right, defining, having some properties, which I will now go into now, some special properties, standard properties related to the action, making it possible to define cochains. So as an example, which is most commonly used and studied, is a flat manifold or a fine manifold or locally fine manifolds. These manifolds have many names in differential geometry. So we have a manifold with a flat connection D, and we define the product on the sheaf, let's say, or the space of sections or vectors, vector fields. So X and Y are vector fields. We define the product by the action of the dxy, where the D is the flat connection. Because of this torsionless and curvatureless, the curvature vanishes, you see this product has very nice properties, and it defines precisely a structure in Castle-Wilbeck algebra. So we can tensors is degraded by the degree, P and Q, and the space of tensors is a two-sided A module. So we can define twisted cochains. So we have this special product, and while satisfying this, you see special conditions, Kiwi conditions, and we call this key Kossel-Weinberg module structure as a two-sided twisted Kossel-Weinberg module structure. And we denote such a vector space W with its tau subscript tau, or T, twisted, four twisted, let's say. Well, this permits us to define several types of cohomology. Perhaps due to a shortage of time, perhaps I will not go into the details. I will give you later. You see the reference where all this is well explained and calculated. Anyway, there are several. We can define the standard Chevalier-Eilenberg complex and cohomology for the associated Lie algebra L script A script L. And we can define we can define Kossel-Weinberg cohomology for the algebra A, Kossel-Weinberg algebra with values in this W two-sided module. So in degree less than 0 we have this 0, in degree 0 we have WT, and in higher degrees we have homomorphism, a linear homomorphism from the tensor product of A into W. We have a special differential operator. You have here a formula for this operator. With the star operator, with this, you see W here is this partial I, it's omission operator, and so on and so on. So the important is the result, I would say. In such a short time, I would not explain too much details. So it's that's the graded cohomology we have here, and the graded cohomology admits a subcomplex whose cohomology coincides with the Chevalier-Eilenberg. So it's a kind of extension, and especially important in the last blue theorem on this page. Because when we calculate the second cohomology space, this O, says is a kind of reduced, because CO with the subspace of C-infinity cochains of order 0. So the special cohomology associated to our Kossel-Weinberg algebra of the affine manifold M-nabla contains the Delan cohomology and something more. That something more is important because it permits to introduce into the theory foliations. So here we have this. This cohomology is an invariant, so it's invariant by global affine transformations of the flat affine connection. And we introduce this Betty number of this flat affine manifold, let's call it, that's a dimension of the corresponding Q cohomology is greater than the classical Betty number. So here below you have the reference, a recently published paper in the proceedings of the conference dedicated to the 60th birthday of Professor Baniaka. I believe it's free online, this volume. Okay, so let's pass to the foliations. That's the main topic, I would say. I would stimulate your interest, your appetite in foliations, in information geometry. What is a foliation? So let's say the English name is less explicit than the French one. The French is feuilletage. And the English comes from Latin, folia, and the Latin is not very popular, so I don't believe you have any idea what it is. So, when I prepared this talk, I had some problems how to explain you simply what the foliation is. But fortunately, you have published this magnificent volume of proceedings. You have all this volume. It's a perfect example of a local foliation. When you forget about the spine, you have a lot of sheets of a book parallel to one another. Actually, it's a local example of a foliation of a three-dimensional space by two-dimensional objects, which are called leaves. Well, I can draw you a foliation of feuilletage. The foliation theory, it's a theory developed in France. One of the fathers is Georges Repp from the Strasbourg University, and he produced a very nice example. So let's take a plane and draw a parabol of the equation y equals x squared. Then you see transport vertically the parabols. You have a family of parabols not intersecting one another, which fills the plane. Then compress it into the vertical strip. So you have these parabols, give you a kind of parabol-like curves, filling this strip. When you rotated the strip along the middle axis, in the middle, you get something more complicated. You have a three-dimensional object. You have a cube. Filled by such paraboloid-like objects. Topologically, we have a cube as a boundary filled by planes, because these paraboloid objects inside are planes, topologically. So, let's do another step. Let's cut it by two planes. We have a bounded objects. We have a solid tube filled by planes with two discs at the top and at the bottom. When you glue it together, we get a solid torus. What's inside? Inside you have planes. Sorry, I'm not good at drawing, but try to imagine you have a plane inside. But when you look at it, it's like each plane is like a snail eating itself infinite many times, devouring itself. Well, it's not the end. When you put together two solid tori, you get a three-dimensional sphere. So in the sphere, you have a foliation. The sphere is filled, what's inside? We have one torus, which is the boundary, comes from the boundary, because we glued together two tori together. So inside the sphere we have a torus, and outside we have two connected components, each of them filled by planes. It's a famous rare example. But if you consider it too abstract, I have another possibility, perhaps much pleasanter. Well, it's a kind of story of the mythology of the Foliations theory, and perhaps it explains why Reb chose such an example. He had a sweet tooth, so he was very fond of cakes. And one of his favorite cakes was so-called foliated cakes, pâtisserie feuilletée, the gâteau feuilleté. So perhaps after the conference, go out and search for some famous pâtissier de Paris and look for foliated cakes. And you can just savor both mathematics and your palate. So you have two pleasures at the same time. So let's go, let's say, further on. I hope I have convinced that it's very nice to study foliations from 2 points of view. And perhaps Paris is one of the best places to do it. Well, so let's go to so, and here when you have this additional object, you can define precisely foliations. There are some details, some technical details which make sure that it can be done. Well, I can skip this slide because it is a definition of the Fisher metric. So about the dual connections, I believe we have already heard. So it's not so important. But here is the important theory. So on every local flat manifold, whose two-dimensional twisted cohomology, which I defined earlier in the talk, differs from the Graham cohomology. So it means that we have this something additional in the cohomology defined earlier. There is either this manifold is either a pseudo-Riemannian manifold, or it is foliated by a pair of georthogonal foliations for every Riemannian metric geodesic. These foliations are totally geodesic. What is totally geodesic? Because the foliations have these leaves, you see level sets, like the pages of your book, of our proceedings. With the relation, these submanifolds can have some different properties with relation to the metric, to the Levi-Chiltern connection, or to the flat connection. And in this case, we say that it's very nice. Being totally geodesic is a very important and strong property. So, fortunately for us, it can be shown that these two foliations, which appear naturally, you see, are totally geodesic with respect to this dual pair of connections. So here you have some more. You see, these dual pair have some special properties. Then you see when you average in some way, we obtain a unique torsion for a linear connection which preserves both foliations. So what about the properties? Having these foliations, we can say quite a lot of things about the manifold itself. For instance, the universal covering can be a product of these components of the products are the universal covering of leaves. We have a lot of, we can say a lot of things about the, you see, properties of leaves, about topological properties of leaves. We can, in low dimensions like 3 and 4, we can try to determine the, you see, or classify even, perhaps in the future, the manifold itself. So perhaps I should stop here because, so, merci pour votre attention. Thank you.